Hello, my name is Wilson Perlaza. I am a student Technical English 2. My project is Hydropower Plant Model Simulations in MATLAB Simulink. Introduction. Hydropower plants convert the potential energy of water heat to mechanical energy by using a hydraulic turbine. The hydroturbine are interconnected to generator that convert the mechanical energy to electric energy. The hydropower plant is basically made of a generator, a turbine, a penstock, and wick gates. Generally, two types of turbine are used: impulse turbine, for instance Pelton wave turbine, and reactor turbine like Francis and Copeland turbine. The generator and turbine are mostly connected directly by a vertical shaft. The existence of high height produces fast low wind, weather that flows through the penstock and arrive to the turbine. The flow of water into the turbine is controlled by the wick gate. Wick gates can be adjusted together with the opening of pivot around the periphery of the turbine to control the quantity of water that flows into the turbine. Servo actuators controlled by governor have to adjust this gate. The water drive the turbine generator set, and the rotating generator produce electricity. At the initial stage, the storage water with clear hydraulic heat possesses potential energy. As it flows through the penstock, is gradually lost potential energy and gain kinetic energy before reaching the turbine. A critical look at the process of energy generator by hydropower plant showed that hydropower plant model are highly influenced by the penstock turbine system, the electric generator, and numerous control systems. Model of hydropower plant. An extensive review of the modeling of hydropower plant is handled at this level with the help of a model of hydraulic turbine designated by IEEE Working Group 1992 under MATLAB simulation software and available on the Macworld website. The model is first described and further modified and simulated. The hydraulic turbine and governor block implement a nonlinear hydraulic turbine model and PAD governor system. For example, circuit in MATLAB projections. Summary. In summary, analytical models of hydropower generator were first reviewed. These models were revealed inadequate for the proper modeling of the dynamic aspect of flowing water, gate controlling, and other. System simulation was further reviewed, and a common objective of the latter types of modeling was to look at the span variations the generate power and its stability and dependency on input parameters such as opening and closing of gate, which relate to the speed and amount of water following to the turbine, penstock, turbine, and generator modeling. The review showed that modern system modeling adopts software simulation approach among with MATLAB Simulink software and riverware can be cited. Video. Below a video to the complement the explanations.
Hello, my name is Michael Luciano, and I'm here with Stephanie Lopez, and we're going to talk about our hydroelectric generator simulation using MATLAB Simulink.
First, go over the layout we have. The main components of the block diagram are the power GUI, the synchronous machine, our hydraulic turbine and governor, and the excitation system. We have our feedback loop here and a couple of scopes here with a gain converter because all the signals coming from the bus selector are in per unit, so we have converted them back to SI units.
Okay, so to start, we're going to talk about the power GUI box. This is what initializes our system, and this box is also used for a lot of other complex parameter changes and calculations that you can use for a lot of other things. As you can see here, there's a lot of things you can mess with, but we're going to focus on the machine initialization. So you can see here that we have a bunch of the machine info, and this is where we're focused here. We want a PV generator, power and voltage, a 13.8 kilovolt terminal voltage, and 150 megawatt active power. We also want the machine initialization frequency to be 60 hertz so that it can be synchronous with the grid. And when this is all set up, we click compute and apply, and it takes a second to update everything. When it's computing and applying, it changes various parameters in the generator and the turbine and the exciter. It sets the reference values and also changes some of the initial conditions and the resistance and reactance values inside the systems. And when it's initialized, then we can talk about the next thing.
Okay, so I'll run through some of the aspects of the synchronous machine. We used a three-phase synchronous generator. It's set to 200 MVA, 13.8 kilovolts, and 60 hertz. The inputs are the mechanical input here from the turbine. We have it set to power. And then also for the field voltage, which is connected to the excitation system here. The M output is a data bus that sends out various measurement signals from the system to a bus selector that are then either sent to a scope, or we have them looped back to the two initial systems that we're using. These here are just the terminal voltages that we have sending out to a distribution system. So when you open it, this is the initial configuration. We have our mechanical input set to power. You could also do speed or the rotational torque. Salient pole for hydroelectric generators. These are some of the specs. This is where we set the initial parameters, and the reactances, resistances, and initial conditions here are all affected by the GUI, so we don't have to touch it too much. And then in the load flow, we have a active power generation of 150 megawatts, and this helps the GUI to set the initialization for the power load.
Next, in the hydraulic turbine and governor system, we see we have 5 inputs here. This is the rotation reference, and this is the power reference. This is in per unit values, so we reference the rotation to 1 and the power to 0.75. These reference values are actually found by the power GUI, so these were not set by us. This is set by the GUI so that it can reach a steady state. When you mess with these numbers, we notice that it really doesn't change the shape of the graphs, the data graphs of the output. It just changes how fast the system actually reaches steady state. And for the other inputs, we have here, these bottom 3 come from the feedback loop from the generator, and you can see here it's our output active power, our rotor speed, and our rotor speed deviation. These parameters go into the hydraulic turbine and the governor system, and they tell the governor to open or close the wicket gates inside the turbine, and the wicket gates are responsible for controlling the amount of water that enters the turbine, and that in turn affects how fast the turbine will rotate. So if we click on the hydraulic turbine, we see we have a lot of parameters about the servo motor, the gate opening limits, drooping regulator, the actual turbine, and the initial mechanical power. This is all taken care of by the power GUI. And next, for the excitation system, we have another reference voltage in per unit values. That's why this is 1. This is also taken care of by the power GUI. And we have 2 inputs here. It is the stator voltage on the D and the Q axis. These also come from the feedback loop from the generator. And if we click on this, we see more parameters, and again, these are all taken care of by the power GUI.
Okay, so now we are going to actually run the system. It'll take a minute to compute. So the first graph I'll talk about is the field voltage, which is coming from the exciter out of the synchronous machine. So you can see when it first kicks on, there's a spike in the voltage being delivered before the automatic voltage regulator corrects the fluctuation and the system begins to stabilize. Next, we'll look at the terminal voltage here. And again, the system starts a little over 1, and then due to the fault, spikes down to around 0.4, and then quickly begins to stabilize again.
Now for the speed, we're going to see that this is in radians per second, and it spikes pretty fast, and then because of the fault, and then due to the feedback PID system, it will reach a steady state at about 377 radians a second. And then next, for the stator current, we can see all 3 phases here, and at the initial startup, we see the reaction from the fault, which is a big spike, but it only lasts for a short duration of time before the 3 phases come back and stabilize in between about 10,000 amps. And then finally the output power. We see the fault reaction of noisy power that lasts for about a half a second, and then as the PID system corrects it, we see it stabilize steady state at about 150 megawatts. So in conclusion, with our synchronous generator and our hydraulic turbine and governor and exciter system incorporated with a feedback loop, we can set the parameters to reach a steady state at any output power that we want, in this case 150 megawatts, and we can observe the speed at 377 radians a second, or about 3600 RPMs, and also the stator current. We can see the AC current reach 10,000 amps. The terminal voltage, we can see the AC voltage reach 10,000 amps, and the field voltage we can see reach steady state at 10,000 volts. I meant to say volts for this one as well. But anyways, that concludes our simulation. Thank you very much.
Hydropower plant diagram complete. What considerations to all the components described previously in figures 3, 4, and 5. The final model of figure 7 is built and simulated under MATLAB Simulink. The model consists of a synchronous machine associated with the hydraulic turbine and governor HTG and excitation system block. The model is extracted from MATLAB 2012 examples and modified to serve as an extensive review on the hydropower plant. The model is made of 250 MVA, 14 kV, 3-phase generator with a nominal speed of 112.5 RPM that is connected to a 161 kV network through a delta E H Y transformer rotate 300 MVA. Thank you.